Let us move on to the next speaker. He is Aditya Makwana. He has done his BSc Mathematics. He is in BSc Mathematics Semester 5 from Maharaja Sayaji Rao University of Baroda. His topic for today is pointwise convergence of sequence of functions. So, Aditya, over to you.
Yes, ma'am. Is my screen visible?
Yeah, it is visible.
Okay. So my topic is pointwise convergence of sequence of functions. In this topic, I will discuss first what is sequence of functions, and then what is what does it mean to say that it converges pointwise, and then few examples, and finally I will summing up all the things. Now, sequence of functions. For sequence, for function, we need to define a function. So let E subset of R, if for every positive integer n, there is a function fn whose domain is E and range is R, then it is denoted as sequence of function fnx is called a sequence of function defined on E, where elements are f1x, f2x, and so on, where x belongs to E. Now the question arises over here is, as we know, sequence is a function from natural number to real numbers. So what is domain of sequence of functions? Can anyone guess? Okay. So intuitively, I guessed was it should be natural number, set of natural numbers. But it is not like that. The domain of sequence of function is set E. So, for example, let fnx is equals to nx. It is just a notational things that sequence of function is seen like this. Fnx is like x, 2x, 3x, and so on, so on, so on. Now, pointwise convergence. So, it is basically uh, convergence we have to define in such a way that we have to check for each x belongs to the domain, which is set E. So suppose that f of x and f of nx is a sequence of functions, then pointwise, then fn tends to f pointwise on a if fnx tends to fx as n tends to infinity for every x belongs to a. So we say that sequence of function converges pointwise to the function f. Now let us take some examples. So I have taken first example and defined fn in such a way that domain is close 0 to 1 to r, and fnx is given by x raised to n. So algebraically, if x belongs to 0 close 0 to open 1, then x raised to n will come will become a geometric series which converges to 0 as n tends to infinity, because ratio is less than 1, and for x is equals to 1, x raised to n tends to 1, as xn is a constant sequence 1. So we can define the pointwise convergence fx in such a way that 0 if x belongs to close 0 to 1 open, and 1 if x is equals to 1. So let me show you one geometric approach. For a graph of x fx is like this: f1x is equals to x is a straight line. Then in this graph, it is clearly seems that the points are tending to somewhere. As n increases, the graph for each point in 0 1 is going to somewhere. So for every point, it is convergent. And note that although fn is continuous on 0 1, but their limit f is not continuous. It is just a note. We don't have to do it with anything. So pointwise convergence does not in general shows that the function, the limit f is also continuous. So let us take another example. So I have taken an example of fnx is equal to sine nx upon n. So algebraically we know that sine ranges to -1 to 1. So mod of sine x is always less than or equal to 1 for any x belongs to R. So over here to estimate fnx, I have used one property. Can anyone guess that? Okay, so I have used Archimedean property. So Archimedean property states that for xy belongs to R, if x is greater than 0, then there exists n belongs to natural number such that xn is greater than y. So for fnx greater than 0, it is always greater than 0 because it is mod. And for 1 belongs to R, there exists an n positive integer such that fnxn into n is greater than 0, greater than 1. So I have just shifted n to the left side, and I have this function. So as n tends to infinity, it has to tends to 0 because 1 upon n tends to 0. So we conclude that f of n converges, the sequence f of n converges pointwise on R to the 0 function. So it is geometrically it looks like something this. So here also note that if fn tends to 0 pointwise on R, it doesn't means that fn sequence of the derivatives of the function also converges. So the definition I can sum up right now like that: pointwise convergence of sequence of function. So we have seen in each of the cases, we identify the limit of function as the limit of sequence, and if the sequence is convergent. When we want to prove the pointwise convergence, let epsilon greater than 0 be given. Then we want to find nx such that for all n greater than nx, we should satisfy the following property, that is fnx mod of fnx minus fx is less than epsilon. So this show that in general nx depends on x, the point from the domain, which is the set E we have defined initially. So and the sequence itself depends on x. The definition of pointwise convergence when cast in terms of quantifiers, it is seen like this. So we say fn tends to f pointwise on x if for all x belongs to capital X. Here I have taken the domain capital X. So for all x belongs to capital X, for all epsilon greater than 0, there exists a natural number such that for all n for all n small n greater than the capital N, mod of fnx is fnx minus fx less than epsilon. So this is pointwise convergence of sequence of function. So I have given some another example you might try. So yes, so my references, I have taken this examples and theories from book Real Analysis by Professor S. Kumresan and Ajit Kumar, Principle of Mathematical Analysis by Walter Rudy. Thank you.
Yeah, thank you so much